let's get started. Just a few reminders before we start. There's a homework on Canvas due next Tuesday, September 10th. And if you haven't started yet, after class would be a good time. It's about decision trees. We've almost covered everything we need for that homework. I was hoping to finish decision trees in the last lecture, but we'll get it done today and talk about a little bit of linear classifiers, which should be enough for the homework. If not, the linear classifier question is going to be an easy question that even after Tuesday's lecture you should do it. You should be able to do it. But let's hope we get it done today. Another announcement is about projects. Like I said in the last lecture, there's some information that you need to give us about your project theme or what you plan to do for your project, what kind of a project. This should not take too long. It's literally just checking a box and optionally putting some words on the page, like 3 minutes of your time. Of course, you need to think about which box to check, so that might take a little longer. Do get it done, and if this is like worth a tiny fraction of your project point, but more importantly, it will help us organize things for you when the project gets going. So, any questions about any of these things, homeworks or project? Have people started the homework? Have people finished the homework? Are there any questions? Yes.
Is it mandatory to have a partner for the exploratory project?
No, it's not mandatory to have a partner for the exploratory project. So you can convince me that you can do it alone. If it's the kind of thing that typically an exploratory project that ends up being solo is I'm doing this for my PhD. And I'm going to take a little part of it and make it a project. This company, and this is proprietary data that I cannot share with other people. And things like that. Other questions? More questions? There must be questions. There are usually. If not, I'm going to just go ahead and continue with our lecture. Please do take advantage of office hours, by the way. If you don't have questions, please take advantage of office hours. I know my teammates enjoy it when a lot of people show up. I definitely do. So it's useful. There's a question.
One of the questions says type the error on the training set.
Yes.
From my understanding, if you build a full tree, you should have no errors, right?
That is right. That's a good sanity check. That's a good sanity check. It's in fact, for decision tree, this is a good unit test. If you have a decision tree learner, and this applies to very few learning algorithms, where you can train it and then test it on the same data you train on, and you allow the tree to grow arbitrarily large, you should get 0 error. And however, if you have a depth limit, then you may not get 0 error. So there is a caveat there. But yes, that's a good point. Yes?
Is it something related to the data set? Because during the test time, I tried to put just a random number instead of like entropy, entropy, like the biggest information. Just to put a random to see how it goes, and it's always around 90%. So I assume the training set is very good.
Okay, I don't know what good means here. Let's call it easy. So something that I usually try to do is in the beginning of the semester, because we are all optimistic about everything, I try to give a data set that gives high accuracy. Somewhere in the middle of the semester, you will be disappointed with the accuracies that you get. But that is just, it's hard to tell upfront which data set is easy and which is hard. There's nothing good or bad about getting 100% accuracy. That's a different discussion. All right. If there are no questions about homework, I'm going to continue on with decision trees, and hopefully this will be the last time you hear about the gory details, and then we'll revisit decision trees a bit sometime in the middle of the semester. So, what we saw in the last lecture was we looked at the whole entropy based criterion for constructing decision trees. We looked at the ID3 algorithm, and hopefully now all of you are experts on that. One thing I should point out is that's not the only algorithm out there for decision trees. Even the general skeleton of ID3 can be modified here and there, and many of you came up with interesting tweaks that you can change, you can introduce into the algorithm, which, if you think about it, is actually a different algorithm. The way you choose the defaults, for example, if one person chooses defaults in one way, another person chooses defaults in a different way, there's no guarantee that these two algorithms will produce the same tree. So these are minor variants. But a big criterion that exists in the algorithm is how we measure disorder. And that there is, while the original algorithm from Quinlan introduced an entropic criterion, information gain, as defined by Quinlan, was defined using entropy as a measure of disorder. But there are, it turns out, other ways to measure how much randomness or how much noise or how much information there is in a data set, and I'll show you one of those. And in your homework, you have another one of those. And if you read around, you'll find many more. One other question we'll look at is how do we handle examples with noise? This discussion is not necessarily related to decision trees. It's applicable to any learning algorithm, but since we are looking at decision trees, let's look at this. I'm going to skip the discussion about non-Boolean features. The slides are online. Oh, that's a general thing, by the way. I'm not sure if everyone realizes this, but the slides for all the lessons, all the lectures are online. They are on my website, the class website, not on Canvas, but there's a link to that in an early announcement on Canvas. And you can read ahead. But anyway, so I won't talk about non-Boolean features mostly because we've already talked about it quite a bit. And even in your homework, if you think about it, you have some non-Boolean features which have been discretized in a way that we chose. That's not necessarily the best discretization, not necessarily the worst, it's just a choice. I want to spend a good part of this module talking about overfitting and how it's going to be the curse that affects us anytime we use machine learning. So let's get started with decision trees variants. Like I said, information gain is a function that uses entropy to measure disorder. If you remember, information gain of a data set and an attribute is defined as the entropy of the data set minus the expected entropy of each of its partitions as split by an attribute. Right? The important thing here is information gain is defined in terms of a function. If you change the definition of H, you get a different information gain. Entropy is just one of these measures of disorder. We can choose others. One example that's actually rather intuitive is called majority error, which says, let's say you have a collection of examples. I'm going to use a made-up data set here. Let's say you have a collection of examples with features x1, x2. These are all many features together. Like in your data set, you have 22 features, 21 features. And let's say this one, the first example has a label plus, plus, minus, then plus. Now, of course, this has slightly more entropy than a data set that has all pluses or all minuses. The question that majority error is asking is, If you let the tree grow all the way down, this will at least need one more split. You split on x3. If x3, or you split on, it will need at least one more split so that this example is separated out from the others. But what if you were forced to stop growing the tree there? At that point, if you are forced to stop growing the tree, you have to pick the majority label, which means you'll get 3 out of 4 right and the fourth one is wrong. So the majority error is the error of the majority label. If the majority error is large, so now let's consider 2 cases. Let's say we have this and, oh actually, you know what? Yeah, let's take this. And I'm assuming in that, or if it's a tie, I'll randomly pick plus. So the majority error for this case is the majority accuracy is 3 out of 4. So the majority error is 1/4. Whereas here, the majority accuracy is half and the majority error is half. Which means this thing has more disorder. In some sense, majority error acts like another measure of disorder. And I'm not going to talk about the relations to entropy, but I encourage you to think about how, if you, what would be the majority error for equal probability distribution. I've already, the slide already has the answer. Or what would be the majority error when all examples have the same label? What would be the majority error when all examples have the same label? 0, because majority is everything. So this is just another way to measure disorder, and the way you use this inside the information gain inside the ID3 algorithm is to essentially replace the original measure of disorder. So where we used H, the entropy, you would plug in the majority error, and that gives you a different variant of ID3. Now, there are a few interesting things to think about. So, essentially it works exactly like entropy, and I have an example here. So, at some node you have 15 pluses and 5 minuses. So, 3/4 of the example, 3/4 of these examples are plus, which means the majority error is whatever is left behind. So, it's 1/4. It's the error of picking the majority class. This also works if you have more than 2 labels. If you have plus, minus, and let's say 0, and there are 15 pluses, 5 minuses, and 3 zeros. So let me write it down. If you have 15 plus, 5 minus, and 3 zeros, so that looks like 30. Let's put, let's say, 3 stars. So the majority class is still a plus. So there are 23 examples, and 8 of them will be wrong if you pick the majority class, which means the majority error is 8 over 23. So I encourage you to think about how this relates to entropy. In your homework, there's another variant, not majority error, but the Gini index. Now there's an interesting reason for why that shows up in the decision tree universe. Historically, these classes of algorithms like ID3 were developed in the 70s or 70s, and almost simultaneously another group of people, statisticians, Jerome Friedman and I forget his name, and this person's name I forgot in office hours too the other day. They came up with another class of algorithms called CART, classification and regression trees, and the Gini index plays a big role in those families of algorithms. But they are essentially very similar algorithms. Any questions about any of these things?
So, for example, if the problem was of data segregation, could we do something similar to variance or something?
You could. In fact, this was a connection that to variance that someone came up with earlier in the lecture. It requires some thinking, but that's possible. Yes. Other questions? No. Let's go to the other practical point. Let's say that we are collecting data, and we find that on day 8, the humidity sensor broke down. And so we don't have any data. Of course, we didn't play tennis because we didn't feel like playing tennis that day, but we have the label, but we don't have the feature. This can happen. This happens very often because when we are collecting data, there's no guarantee that all our data will be available. Now, what could you do? Can people come up with ideas? What would you do if you don't have that example? Yes.
You treat it as what the majority label would be in the data set.
Okay,
Just
so
assume that it's going to take the most common one.
most common in the data set.
Yeah.
So one answer, which is a perfectly valid answer, is to say the most common feature value. So in this case, it will be 5, right? That's perfectly reasonable. It's a good heuristic because it's most common. The chances that it's the safest thing to do. Any other ideas? Yes.
Could you also go and look at, because you have the label, and then from that label, go back and look what the most common value is that gets that label?
So you look at all the labels that correspond to that example, all the examples that correspond to that example, that label, thank you, and you look at the most common label feature value within those things. It just so happens that that's also high. But that's another perfectly reasonable thing. What you did is essentially impose some extra information that says these examples are somehow alike. As a result, they should share that attribute. Yes?
You give it its own branch.
You could give it its own branch as unknown. You basically create a new feature value called unknown, but that's a slightly risky proposition. Because what you might end up doing, so first of all, when I say you could, of course, nothing in the algorithm prevents you from doing it. You can create a new value called unknown. Now, this is something that is not a machine learning point, but it's got something to do with feature engineering. If you create a branch called unknown, what you are essentially saying is humidity can either be high or normal or unknown, and the fact that it takes unknown has some correlation or some influence on whether I play tennis or not. Whether the sensor breaks down or not should not decide whether I play tennis or not. So it's essentially introducing a causal link between the sensor breaking down and me playing tennis. In this case, I might say that's not a reasonable assumption, but there are certain other domains that that's a perfectly reasonable assumption. So the point there is there are multiple ways of fixing this question, fixing this problem. Each way in which you address this question introduces some information that you are bringing in about the domain. Yes. First you then.
Can we build a separate decision tree to classify the missing label? Or missing feature?
Using other features?
Yeah, including the label.
That's a very cool idea. I think that's clever. Where you might run into problem is what if every row has something in it. At that point, it can be a combinatorial line. But I think that's clever. Yes. Yeah.
If there is only one example in big data set, I can just drop that row.
That's true. In fact, I'm surprised that nobody said that. Imagine you have millions of examples. For some reason, I have played tennis millions of times, apparently. If you have millions of examples, you don't lose much by dropping a row. On the other hand, there's also something to think about, the cost of creating data. Sometimes it might be expensive to get data. Sometimes you might actually have to shell out money. Sometimes, for example, certain data sets took years to create and involved many PhDs spending a lot of time. There, you don't want to drop anything. Once again, it's a design choice, right? So, were there other? Yeah, one more. Yes.
And what if we consider the possibility that the other features are at least partially related and look and see, like in this case, look at other cases where it's sunny, mild, and we want the humidity.
Right. So essentially, this is very related to the other suggestion where you use the other features to predict this value.
Yeah.
Right? And that all of these, so there were 3 suggestions which are essentially very similar in the sense that by using the other features to predict this value, what you're saying is that the features are not truly independent of each other, and as a result, then as a group, the features together carry enough signal to kind of fill in these values. I mean, I don't know much about weather, but I think that's probably right. But in certain domains, that may not work if your features are all completely orthogonal to each other. Which means there is no information about any one feature using the other. Which means you need all the features and you can't fill in the rows. Maybe it's possible. I have not seen a single data set where that is true, but you have to be aware of that. Yes?
Could you add examples, one each with each of the possible values?
Oh, in fact, that's a more subtle suggestion. You can add examples where you have, let's say you create 8A and 8B, which has the same values for all the features that are known. So this is weak, and then this is the same, and you keep the same label, and you put a high and a normal. So you've essentially doubled it. I'm going to argue that this is dangerous, except a version of this is awesome. A variant of this. The reason this is dangerous is you are creating 2 examples and you're saying it's equally likely that humidity can be high or not. But what if humidity is, let's say we live in Salt Lake City, humidity is high maybe 1 in 100 days and it's normal 60 in 100 days. By creating this sort of an equal split, you are essentially saying that you are amplifying the low frequency features. And so you are changing the distribution of the data. This is a dangerous thing to do because by changing the distribution of the data, you might introduce artifacts in the prediction engine. So that's risky. Yes?
So if you know that the humidity is high 33% of the time, you introduce 3 rows and then replicate that sort of probability.
This is the slightly more awesome version of this that I was going to talk about. Instead of saying, if you knew that humidity was high 33% of the time and normal 66% of the time, you could do this by introducing 3 rows of this kind and no, the other way around, 1 and 2. Something. You introduce as many rows as the proportion is maintained. That's a good idea. The dangerous thing about that is, remember, we are counting things for entropies, and by essentially growing this class of examples, you are artificially amplifying the other features. Instead of introducing the rows, what you could do is you can have fractional values in this feature. So instead of saying this is, instead of saying that this is say fully high or fully normal, this could be 3/4 high and 1/4 normal, adding up to 1. It's a feature that is those of you who like. I'm not going to give a physics analogy. This is essentially the feature value is a fractional value. I don't know what the feature is, so it's simultaneously both high and normal. It's high with probability 3/4 and it's normal with probability 1/4. And when I do the counts, what I would do is, instead of adding up this, when I do the count, when I have to account for this feature value, I would add up 3/4 instead of adding 1, and for high, and I would add 1/4 instead of adding 1 for normal. So who said that counts have to be integers? Fractions are okay. The math works out, and that will also preserve the relative ratios of the other features. It won't accidentally oversample or undersample other features or this label here. Yes?
So when you make a decision tree, how do you know how to branch when you come to this feature?
Excellent question. By the way, all these suggestions are awesome. Let me just go to a different slide where I've written all of these up. So you can use fractional counts, and one question that you should, so let me just very briefly, I'll come back to your question, but very briefly, you use, this was suggested using the most common attribute, using the most common value among all examples of the same label. There were actually other suggestions which are not here. You can use fractional counts. And then the question is, what do you do at testing time? What do you do with the decision tree when you get an example where a certain feature is missing? And that's the question you asked. Let's go through the whole list again. What do you do when you use the most common value and you see that a certain feature is missing? You can plug in that value there, and this will work. The same thing works for the, you can't do the next one because you don't know the label. So you have to use the first one there. Here, what you can do is you take both parts. If it's high and normal, so let's say, what was that? Humidity? Yes. If humidity is high with 3/4 and normal with 1/4, you store this information in the node. You say that, at this point, oh, sorry, you don't store. You have an example where you plug in this value, and what you do is you take both parts. So you have humidity, you have high, and normal, you take both parts, and you take all the way down, go all the way down to the leaf, you get a label, you get two labels. And now you return a label, you don't return a label, you say with probability 3/4 it's this and with probability 1/4 it's that. So suddenly your labels carry uncertainty. The uncertainty that was in the feature gets percolated down to the prediction. You could do that, or you could say, I don't want my user to ever be exposed to probability, and you just make a decision. You have a follow-up?
So if you do return a label with probability, how do you know what to do with that probability?
That's the problem. That's where at some level we have a decision system. We have to choose. Either you choose the most probable one, or you toss a coin with a bias equal to this much, or you use. So eventually, if you need a decision, you need to threshold the probabilities. You had a question? Same thing. Okay. You have a question. Yes.
So in decision trees, we only for classification we only have the label, right? So we do not have the probability of the confidence.
We don't. No, we don't. In the vanilla system, we don't. If you want probabilities, then the leaves have to become like probabilistic classifiers of their own. Yes.
So after we get two labels, I'm assuming the way I would think you go with the one with the higher probability.
That's the most.
So the reason we use fractional values for unknown attributes is to maintain an accurate calculation of entropy with respect to.
That's right. That's exactly right. Yes. So all of this is nice. The last one is somewhat sophisticated. It may seem very clever, but in practice, the first one works pretty well. This is a repeating lesson that we'll encounter. The super sophisticated things are not always needed. When I have any decision tree implementations, I actually just use the first one just because it's easier to implement, and my data, I don't have to make any changes in my data structures. For this, you need a data structure that tracks probabilities and all that stuff. So it becomes a little bit tedious. Okay. So you use essentially some variant of the same method at test time also. Something about non-Boolean features. I just want to tell you what they are. Remember that the features don't have to be binary. They can take 3 values. It's simple with decision trees because you can essentially have multiple branches. Or you can convert it to binary. This was a question that came up earlier where you convert every path into the decision that, so if the outlook equals sunny, that feature really can be seen as 3 features. Everything in blue is a feature name, and this is feature value. So sunny is true, overcast is false. So I can essentially binarize anything. By binarizing everything, you get tall and thin trees. By keeping the branching, by not binarizing, you can get wide trees that are shallow. You just have to be aware of this because that will change how you use depth limits. For numeric features, of course, you use thresholds and you can discretize, and we spoke about that, so I won't spend time for that. Okay, now let's get to the main feature of today, namely overfitting. To introduce this idea, let's look at this somewhat goofy function that I call the first bit function. It's a Boolean function that takes n inputs and it ignores all the inputs except for the first column and just gives the output is just the first column. Now, one might say that this is such a stupid function to learn, but what if I didn't tell you this was the function? Then you have to spend some computation to actually discover that this is the function. We'll call any feature that is not used irrelevant. So what's it? Can someone tell me what the decision tree for this function? How do you can you describe a decision tree for this? Someone who's never spoken in class. Yes.
Yeah, x0, is it true or false?
Yeah. So you have x0. If it is true, you say true. If it's false, you say false. Now, it doesn't matter how many inputs there are, the decision tree should be the same by definition. Because only x0 matters, everything else is irrelevant. Okay, let's use this function to kind of explore an idea. Oh, by the way, what you should do is convince yourself that ID3 will get you this tree. This is one of these things that's easy to work out, and ID3 should decide to split on x0. If it does not, you have a bug either in your understanding of ID3 or in your code, or somewhere in the mind. As a general rule, I would say whenever you are trying to understand a learning algorithm, come up with a data set that is extremely ridiculous, like this, and make sure that the algorithm does what is advertised on this data set. Because if it cannot handle that, it's probably not going to handle real data. That's usually how I end up debugging learning algorithms, code also, like software that I implement. Okay, now let's say that we have the full, so you have n features, and let's say we have the full 2 to the n rows in the truth table for that function, for some n. Now, let's say you grow a decision tree on this data. What will the error be on future examples? On any future instances when this tree function is used? Yes. Why?
Because we have all the possible values of these features.
That's right. So if you've seen all the examples, there is nothing surprising in the future. If you've seen the entire instance space, you can't see anything that you've not learned before, you've not seen before, and the decision tree algorithm, the ID3 algorithm, is guaranteed to be consistent with the training set. It's guaranteed to be consistent with the training set. That means it will give you the right answer, the right correct label for any example that it has seen during training. And it has seen all the possible examples during training, so in the future it will never make a mistake. So that's awesome. So the decision tree, the ID3 algorithm will find a consistent tree, and the decision tree, there is some decision tree that can represent a function. So this is nice. Now let's make this slightly more problematic. Let's say that we still have all 2 power n examples, but during training, I toss a coin for every example and randomly change the label, something like that. So some falses become truths and some truths become falses. I do this randomly during training, and I do this randomly in the future also, just because I can do it. So what that means is that there might be an example, this example has a label false in the training set, and it could come up with a label true in the future. So same question. Actually, just I did a simulation of this with different values of n, with different from 2 to 15, different number of dimensions, and computed the test accuracy. It turns out that, of course, you're not going to get 100% test accuracy, because there might be an example that does not have the right label, or does not have the same label that was seen during training. So, if you want an interesting combinatorial, interesting counting exercise, you can ask yourself, when the corruption probability is 0.25, why is this number roughly 0.375? It's a fun exercise that you can do on days that you are bored. So the point is that you have that now, but what is the training? So this is the generalization accuracy. This is prediction on the training set. What's the training accuracy? Sorry, prediction on the test set. What's the training accuracy? So, okay, cool. I don't know who's speaking. Yes.
Should be completely correct based on the training data, because training data has all the possible input values. For instance, even though the labels are wrong, our decision tree isn't trained on that. So it should give us all the right values according to the training.
That is correct, actually. So the training accuracy should be 100%, because ID3 does not know there is noise. ID3 does not care there is noise. It will find a tree that's consistent with the training set. It doesn't care. There is no notion that there is a true function. That's something that's a that's an imaginary idea that we have to understand how things work. The algorithm does not know that there is a true function that has been corrupted with noise. It will find a tree that's consistent with the training set, and when you evaluate the resulting tree on the training set, you will get perfect accuracy. Right? So there is a mismatch now. The generalization or the prediction on the test set gives you about 37% error, whereas on the training set you get 0% error. Now what we say then, yes?
What if you have two items in your list and they have all the same feature values but different labels at the end?
In the training set?
Yeah.
Oh, then the ID3 algorithm will have to pick one and it will not have perfect. The training accuracy will not be perfect. Here we are assuming that that doesn't happen. Yes. So, but then the question is, why is the classifier not perfect? And I already answered it, but can someone articulate it? Yes.
This data distribution is not identical to training data distribution.
True. Something more. Or something less, something simpler. Something that is not even. Oh, I've already. Yes.
So classifier is memorized data.
Yeah, that's actually that may be the simplest way of describing it. What typically happens, not just for decision trees, but for many, pretty much all learning algorithms, is if you do not do something explicit about it, and if the hypothesis space has the capacity to memorize the data set, it will memorize the data set. The decision tree hypothesis space has the capacity to memorize any Boolean function, because any Boolean function can be represented as a decision tree. Which means the ID3 algorithm, if we don't do something explicit to avoid memorization, will memorize the data. But memorizing the data set seems like it's a good thing to do, until you realize that every data set you'll ever encounter is going to have noise. Which means not only will it memorize the signal, but it will also memorize the noise. And we don't want that. Right? So does that make sense? When this happens, we say that the classifier overfits the training data. It ends up memorizing both the signal and the noise in the data. As a result, it ends up overfitting. Overfitting is when the learning algorithm finds a hypothesis that essentially is tuned too heavily to the noise in the data. For instance, in the first bit function, only the first feature is relevant. And no other feature should ever show up in the decision tree. We all agree that the decision tree, irrespective of how many features there are, should look like this. But because there's noise in the data, other features will come into play, and neither of these partitions will be pure, the way we defined it. And there will be more, okay, it's a binary feature, you'll not have more than two, but the point still stands. You'll have more branches coming out, and other features that should not even be relevant get into play. As a result, my visual metaphor for this is that the decision tree finds the nooks and the crannies in the data and just fits it. Things that should not be relevant end up becoming involved. What this leads to is that noise is random. Noise can be seen as random. And the noise that you get during the training set may not exist in the future. As a result, performance degrades. If the noise ends up existing in the future, then maybe it is signal. And maybe it's a feature that is relevant, but let's not worry about that happy scenario. Yes?
I'm a little confused about the tree because you said that the 83 algorithm will produce the original tree, which is 2 branches.
That's only in the perfect case. If you have perfect data. So,
if we have noise that can branch off like it did,
it should, right? Because let's actually build a tree for this. Not using ID3, but just eyeballing it. Suppose somehow ID3 still finds x0 as the true feature. So you get x0 at the top node. So you get x0 is true and false. When x0 is true, you are in this half, and now it's not perfectly true. I mean, the label is not all true here. So we still need to branch on one more, and let's say I'm going to branch on x2 here, and when x2 is true, oh, that doesn't work on x. Yeah, basically I need to go identify both that row uniquely. That will lead to 2 more branches, and then on the other side also. So we are getting in deeper trees that should not be that deep. Other questions?
Yeah.
Yes.
So effectively, is it possible to inject some noise in the training data for any classifier and get a more robust classifier? And with small probability.
Why? Why would noise make it more robust?
So we are considering our training data could be noisy, right? And it could overfit to the training data.
Yes.
And can we give it some more noise? Maybe probabilistically.
Oh, so you want to inoculate your data set by randomly perturbing it and trying every possible perturbation and building some sort of an average tree.
Right.
Hoping that your randomness will cancel out the real randomness. What might happen as a result is you could get lucky and it could work, but you could be very unlucky and your perturbation distribution might look nothing like the process that produced the noise.
But the perturbation will be very, very small.
Possibly. So you're thinking about a direction that may work but requires something from the deeper part. Okay, so let's look at a definition of overfitting. This is one formalization for overfitting. This is the first of the many formalizations that we'll encounter. So let's say that the data comes from some probability distribution. This is a probability distribution over the cross product of the instance and the label space. Or to make things simple, let's say there's a probability distribution over the instance space. So there is a certain probability that a certain example will show up. There's a certain probability that a certain email gets written, the exact email gets written. So you can think of a distribution over the instance space. You can think of it, but we don't have access to it. We don't know what the probability distribution is. So there is some maybe unknown distribution. And let's say there is a certain hypothesis space, H, that we are entertaining at this point. Now, it turns out there are 2 notions of error that are important for us to be aware of. There is the training error of a classifier. So given a classifier, let's pick any classifier, little h, that's the classifier that we want to sell to the world. There are 2 notions of error that we should worry about. The training error of the classifier is the error on the training set. How do you compute it? You enumerate every example in the training set, look at the prediction of the classifier H on that example, and look at the ground truth. If they disagree, you lose a point. The error increases by 1. You divide by the number of training examples you have. That's the training error. This is like, an example. That's easy to compute. But the true error of the classifier is, in some sense, a different concept. The true error is something that I have not written here, amazingly, but it's the expected error that the classifier can have on any example according to that distribution. So what you do is you randomly sample an example when I say you randomly sample an example, we can't do it because we don't know the distribution, but it's a thought experiment. You could randomly sample an example if you knew the distribution, and you compute its error, and you weigh its error by the probability that that example can show up. You do it till the end of time, you add up all the errors that you accumulate, and that's the true error. The true error is the error according to the true distribution of the data, which we don't have access to. Now, though we don't have access to the true error of any classifier because we don't have the true distribution, the goal of learning is not to minimize the training error, but to minimize the true error. We don't care about error on the training set. We care about error on future examples, examples that we may have never seen before. And the true error, or it's also called the generalization error, is the error on previously unseen data, on data generated according to the true distribution. Any questions before we get into the definition of overfitting about what the true error is? Yeah.
I know when we were talking about having a test set versus a training set, you said something like 70-30 training test data, but here, if we wanted to actually estimate our probability distribution, we want a larger test set than our training set?
In an ideal world, we want the test set to be as large as possible. Unfortunately, in the same ideal world, we also want the training set to be as large as possible. And that's why we have to build some parameters. In general, we can't measure the true error. Measuring the true error is like asking, I want to know what will happen, what email will show up in my inbox tomorrow. I have no control over that. The test set is supposed to be a representative of tomorrow. It's a representative of the future where the classifier is going to get used. And part of good experimental design is to make sure our test set is big enough. A part of good experimental design, unfortunately, also requires that our training set should be big enough. So, given this idea, so we have two notions of error. There's the training error and the generalization error. And we can compute the training error, and we want the generalization error to be small. Now, using these two terms, we can define overfitting in the following way. Let's say there is a hypothesis H that we have trained. Let's say there's another hypothesis H prime. It's just a competing hypothesis. There are two functions that we are trying to entertain. And let's say our learning algorithm prefers H for whatever reason. You can measure the training error on both of these things. So you can measure error train of H and then the error train of H prime. The learning algorithm may prefer H over H prime because its training error is lower. So maybe H has a lower training error, and that's why the learning algorithm, the ID3 algorithm for example, prefers H. But suppose it so happens that our learning algorithm gets fooled. It turns out the generalization error of H and H prime are actually the other way. So the training error of H is less than the training error of H prime. That's why the learning algorithm prefers it. The training data suggests to this learning algorithm that H is the better hypothesis. But suppose in fact H prime is the better hypothesis according to the true criteria, the generalization. Then we say H has overfit the training data. A hypothesis overfits a training set if it has lower training error than any other hypothesis, but in fact it is objectively a worse hypothesis because it has worse generalization. Now keep in mind this is a definition that deals in hypotheticals because we can't measure the generalization error. That's why we keep aside some data and use the test error as a surrogate for that. And some people end up saying the test error, so instead of putting generalization error in the second criterion, you have test error there. That's a dangerous thing to do because what you might end up doing is you might end up overfitting the test set. Overfitting the test set is terrible because then you have essentially deluded yourself into thinking that the classifier is good, and when it actually matters, it's not going to be good. Yes.
I did not really understand the difference between the generalization error and the test error.
Oh, those are, so the, okay, the test error is something that you can compute using a test set. The generalization error is a theoretical construct that depends on the true distribution of the data.
So, true error that you're not checking on the test data.
So let me, I use these words a little bit confusingly, so let me write down those things. So there is the training error. There's the true error, which is also called the generalization error. That's not going to be enough. The generalization error or the true error. And there's the test error. The training error, as the name suggests, is computed on the training set. The generalization error or the true error is the probability that your classifier is going to make a mistake on a future example, as drawn from this distribution. It's a probability. It's actually the expected error of your classifier. The test error is an attempt to compute that the generalization error using the test set. Right? So the test error is supposed to be like the best attempt at computing the generalization error, because we can't compute the distribution, and instead the test error, we assume that the test data is drawn from that distribution, and using the law of large numbers, if your test data is large enough, we do get the true error. The test data is supposed to be your sort of evaluation of the classifier by on unseen data. Yeah.
So I'm a little bit confused about how we compute the training error, because we have to measure that against the test data.
No, the training error is the error on the training set. So you have the training set, and you can measure the error on the training set. It turns out for ID3, that's always 0, if you grow the tree all the way down. Right? Does it? Okay. But if you cut the tree somewhere in the middle, it need not be 0. So essentially the way you measure training error and test error is the same. You have a data set, the training set or the test set, and you enumerate over every example in the set, and you count how many errors there are. If you do that process on the training set, we call it the training error. If you do it on the test set, we call it the test error. Yeah.
Assume a non-trivial hypothesis space where you cannot exhaustively search over all the hypotheses in that set.
Like decision trees.
For instance, well, it doesn't dimension, but yes. And now you have a hypothesis A, right? How can you show that this hypothesis does not overfit?
We can't show it by enumerating hypotheses. What we can do, and I'm not going to answer that question now, but what we can do is have probabilistic statements with high probability this hypothesis is not going to overfit. That's the best we can do with today's understanding of machine learning. And there's an open question as to how to go beyond that. Those of you who are interested in doing a PhD or getting a Turing Award should solve that question. The bad news about decision trees is that they will overfit. This is a plot from Tom Mitchell's book, where on the horizontal axis is the size of the tree. It's, for some reason, the number of nodes, but you can think depth. The size of the tree grows from here to here, and the vertical axis is the accuracy. So think of this as, you grow the tree and you stop growing the tree if the budget has been met. And what you do, and there are two curves here. The solid line, which keeps increasing, is the training error. And the dotted line is the test error, which is supposed to be a representative of the generalization error. So what seems to be happening is as we allow the tree to get larger and larger, the training error keeps going down, or the training accuracy keeps going up. Why? Because if you allow the tree to grow arbitrarily as large as necessary, it will eventually go to 100%. This is what we know about the ID3 algorithm. But curiously, the test error seems to kind of plateau out and even drop after a certain point. I don't remember which data set this is on, but what this suggests is that there is noise in the training set, and after this point here, the learning algorithm is basically fitting the noise. This gives you a good heuristic for deciding how deep or how far the tree should go, except it uses the test set. In your homework, you don't use the test set, you use the cross-validation procedure to essentially do the same thing, using only the training set. Decision trees will overfit if you let them grow unchecked. On any data set that has any noise, if you grow a tree that's arbitrarily deep, you will end up getting a suboptimal tree in terms of generalization. And that brings us to ideas for combating overfitting. Perhaps the most important idea that you will ever take from this class is that of Occam's razor. Yes?
So would the optimal, go back to the last slide,
yes?
Would the optimal value be where the two cross right there?
It's not, the optimal value is not where the two cross. The optimal value is where this curve is highest.
Okay.
Because we want generalization accuracy to be as high as possible. So the optimal value would be maybe somewhere here, somewhere in this range. Because we want the generalization error to be as high as possible. The place where they cross, there's nothing special about that. Maybe they won't even cross. If you are extremely unlucky, you could end up with a learning curve that looks like this. This is the size, accuracy, and the solid curve could just shoot up and go like this. And the other one could be something like, and that just says that this is a really hard problem. This also, in literally the last lecture of the class, I'll be talking about this same curve, and we'll use these kinds of curves as diagnostics for detecting whether we need more features or whether we are overfitting. This basically suggests that our feature representation is not good enough. Right? So going back to overfitting, maybe the most important lesson you'll take from this class is that of Occam's razor, which is prefer simple hypotheses. That's also a good likeness. Favor simple hypotheses in your hypothesis space. In the case of decision trees, a natural way of favoring simplicity is shorter trees. There are fewer shorter trees than there are larger trees. Right? Which means I can essentially, if I restrict myself to trees of depth, say 3, there are fewer trees of depth 3 than there are trees of depth 300. Which means if I accidentally find a tree of depth 3 that is good, that's a curious accident. It's probably not an accident, it's maybe I've stumbled upon a good tree. So we need this is the intuition that we use to kind of have for doing what you're going to do, what you are hopefully have already done in your homework, which is limiting the depth of the tree. By limiting the depth of the tree, what we do is we are saying that we are imposing a bias towards shorter trees and deeper trees, or longer or taller trees. I don't know how you measure this. Taller trees are most likely going to fit the noise, and I don't want that to happen. As a result, we prefer shorter trees. An extreme version of this is called a decision stump. So I like the way the metaphors here are. The tree metaphor is taken to the extreme. You have leaves and stumps and depth and height and all that. So a decision stump is a decision tree with exactly one feature, with exactly one decision, and with one level rather. And now you might argue that that seems like a pretty awful classifier. You're going to use one feature, and you need to use that to decide whether I should play tennis or not, for example. Turns out decision stumps are by themselves not great, but decision stumps end up being extremely useful when we come to the idea of committees of classifiers, ensembles of classifiers. Ensembles of decision stumps tend to be extremely robust general purpose learning algorithms. Yes?
It seems like it would be easier after you run data on your classifier to fix it and go, oh, I only need this many layers for my tree. How do you do that before when you're building the tree?
So the question is, do you stop growing the tree at some predetermined level, or do you grow the tree all the way down and then prune back? Both of these things happen. In your homework, you're doing the former, by the way. There is I think some machine learning libraries actually do the latter. C5 and C4.5 calls for pruning. You grow the tree and then you start pruning branches. And both of these have pros and cons. The cons of growing a massive tree is that you have to grow the tree, you have to do the whole thing, and then you are essentially wasting work. If you're using this sort of committee of classifiers, you have to grow millions of trees, then it becomes a bit of a complication. But yeah, that's a perfectly valid way of doing things. But irrespective of how you do it, you need an objective criterion for deciding how deep you should go or whether you should prune. And one objective criterion is to use a split of the training set called the validation set. So what you do, and I might be drawing these kinds of pictures all the time. Let's say this is your training data. Every column in this is a different example. So once you have this, what you could do is you have somehow, and let's say these are all shuffled up. There's no order in here. Already, I have decided that 30% of my data is my test set. So this is test, which means my training algorithm will never see it. And ideally, I will never see it because I might accidentally leak some information into my learning algorithm through my head. Okay, so this part is the training set. What you can do is now partition the training set into two parts. And the shaded region here, we'll call this the validation set or the development set, and the rest of it, we'll call it the training set. Everything that's left behind is the training set. What you do is you train your tree on the training set for different depths, and you evaluate it on the validation set or the development set, and you use the one that has the best performance on the development set. Now, can someone tell me what's the problem with this approach?
Yeah, it's essentially the same problem you have with just having one test set.
Yes.
You're always testing on the same data.
That's exactly right. You're essentially, so there are two issues. One of them, what you just identified, is a more subtle issue. So I'll come to that next. The first one is, let's say you have only 10 examples. And now you've already asked me to put 3 away for testing. And now you're asking me to put 2 more away for the validation. And basically my training set is growing smaller and smaller. This idea of using a separate validation set is not awesome if you have a limited number of examples. So that's a sort of a practical problem. The more insidious problem is which is now you might end up overfitting your hyperparameters like the depth on the validation set. You keep trying over and over again, and you find the best tree that's on the validation set, that maybe the 2 examples that you left behind, and you're using these 2 examples to decide the future of your whole project. And that's a kind of overfitting that is subtle but does happen. Overfitting of the hyperparameters. These things like depth of a decision tree, these design decisions that control your learning algorithm are called hyperparameters. And you end up overfitting your hyperparameters on the test set, on the validation set, and that's dangerous. But this is definitely a very, very common strategy when you have large enough data sets. When your whole set of examples is really large, then you have the luxury of getting a big enough validation set, at which point your validation set becomes representative of the true data. If you have that, then that's awesome, and you should do that. And this is increasingly done with deep neural networks, for example, where if you have enough data. Yes?
So couldn't you theoretically train a decision tree and then shuffle the data so that the data you use for the training set to begin with, you kind of restart it and make that the test data, and just iterate, just randomly partitioning it?
This is exactly the idea of cross-validation. So that might be the next thing, but no, it's not. I probably didn't bother making a slide for cross-validation because I wrote copious notes for it in the homework. So cross-validation is exactly that, except what you do is, so you have this set of examples, and I'm not even going to show the test set. There's no, this is the entire training set. The test set is held aside behind the locked vault. We don't get to see it until we have a classifier that we're willing to sell. So what you do is you partition into multiple pieces, 4 pieces, let's say. Each piece here is called a fold. Fold 1. So you have 4 folds here. And what you do is you train on 1, 2, and 3. And you evaluate your hyperparameter on 4. And then you train on 1, 2, and 4. And you evaluate it on 3. You do the same thing, you evaluate it on 2, and you do it on 1. So you do this process 4 times. So you get essentially 4 different evaluations, and you average them out. The average cross-validation accuracy, this is called. So what you can do is now, you can evaluate your hyperparameter. So let's say I have a certain depth I care about. I believe that depth 3 is good. I will run this whole process, compute the cross-validation accuracy of depth 3. And I start building a table. So depth and cross-validation accuracy. Maybe for 3, the cross-validation accuracy is, I don't know, say 70%. Then I try depth 5, and the cross-validation accuracy is 73%. At depth 10, it is still growing, it is 80%. And then after that, at 15, it is 73 again, and at 100, it is 60%. Basically, I repeat this process for every choice of the hyperparameter, and I get a cross-validation accuracy, and I choose the depth, the hyperparameter that has the highest cross-validation accuracy.
So in this case, you would be building 4 separate trees for every depth you wanted to
Yes.
test.
You'll be building 4 separate trees for every hyperparameter choice, and if you have more than one hyperparameter, then you have to take the cross product of all the choices. Each one of those is used. If you have, usually people use 5-fold cross-validation. I don't know, 5 is a good number, I guess. So you do, in this case, 4. You build 4 separate trees for every setting. Let's say you want to also, another hyperparameter, let's say, is should you use majority error or entropy? So this could be for entropy, and you do the same thing again for majority error. So you do 4 trees for every row here, and you compute the average. You can also compute the standard deviation if it makes you happy. And this seems like, at this point, now you understand why machine learning requires so much compute. Because cross-validation is like the standard procedure for finding out which hyperparameter choices are good. Now what do you do once you determine, let's say, that this choice is the best choice? What do you do with these things? Now let's say, at this point you have somehow determined that entropy with depth 10 gives me the best cross-validation accuracy. What you do is now, you put back all the training data that you had into one big collection and train a tree with these choices, and that is the tree that you're going to sell. That's the tree that you're going to evaluate, and that's the best decision that you can make. The cross-validation accuracy or the cross-validation error is a statistically robust measure because it's an unbiased estimate of the test error, of generalization error, which is why it's a good criterion to use for deciding on hyperparameters. Yes.
Is there still a risk of overfitting hyperparameters?
Oh, for sure. There's always a risk of overfitting hyperparameters because you only have that much data. So, of course, you run the risk of overfitting hyperparameters. This is a better way than using validation. It's obviously a better way than using the test set, and it's a better way than random guessing.
So at what point does the test set come into play?
The test set comes into play when you are done with the entire training process. So usually the training pipeline involves first, I'm not going to write because it's going to be a long pipeline. First you decide on your hypothesis space. decision tree or a 20-layer neural network. This choice could also be a hyperparameter. You decide on your learning algorithm, and then you perform cross-validation. Now, once you perform cross-validation, after this really long process of cross-validation, you get a certain set of hyperparameters that are the best. Then you train using the particular algorithm that you choose, using these hyperparameters, and you get a classifier. At that point, we declare training is done. Then you can evaluate your classifier on the test set once, and only once. Because if you do it twice, you run the risk of overfitting on the test set. So I would suggest try to minimize the number of evaluations on the test set. One of my collaborators, for example, insists that we keep the test set for any task that we are doing in a compressed file that we don't even read. We don't write code that reads the data, because what if we accidentally leak that information? And the day before or the week before the paper deadline, we run the test set, we run the evaluation on the test set, and if it doesn't work, there is no paper. But that is science. That's honest.
So when you get the measure of accuracy on the test set, basically all that tells you is how well you think that you built your tree, and that's all the information that it gives you. You don't use it for any further.
You use it to sell with your classifier. You say that if you did all of this experimental process correctly, then the test error is a good estimate of generalization. That's the error that's the measure that you use to go out and say, look, this is the quality of my classifier. There was a hand somewhere here. Yeah.
So are you not allowed to make any other changes to the classifier after you get that data?
Ideally, yes. But in practice, unfortunately, given how expensive data collection is, it ends up looping. And that is a dangerous process, because once it loops too many times, you have overfit the training, the test set. Yeah.
How about, so for instance here, we have a couple of those, right? Like 5, right? 5 different parameters.
10, because I did not write majority error. Yeah.
But okay. And for instance, so we compute those accuracies, and then you said we pick the best one and use it, right, for the rest of your cycle. How about like picking 3 best ones, top 3 of them,
okay,
and then use them to have a weighted.
Yes, but then if you're doing that, you can do that in a more systematic way using algorithms like boosting, which we will deal with right after the break. Boosting is a systematic way of doing exactly that. Okay, this is an important point. So yes, I would recommend that. That way the numbers are comparable. And that's why for all your homeworks, we will give you the folds, just so that there's no random effects that have to be that we have to worry about. So cross-validation is an important idea. Cross-validation is an important idea that is going to pervade through the semester. You should implement cross-validation ideally in a way that is independent of the learning algorithm being used, because you'll be using it throughout the semester. And you'll be using it for your project and hopefully for the rest of your life. The one nice thing about cross-validation, there's not too much nice to say about it from a computational point of view, because it is a chore. The one nice thing is that it is trivially parallelizable. Those 4 runs are all independent of each other, so you can parallelize that in different CPUs. Every hyperparameter choice is also parallelizable, because this run is different from that run. So every fold of every hyperparameter choice can be run in parallel. So it is trivially parallelizable, which is why if you are running a company like, say, Amazon or Google, you can farm out cross-validation across the entire cluster that you have, and you can do this process rather fast. Another choice is the point that came up before. You could grow the full tree and then prune. But then you have to decide how to prune, what's the criterion for pruning, which means you need another data set. You could use cross-validation or validation again for pruning. But pruning is slightly more tricky. The version of pruning that's used in C4.5, I think, is actually to convert a decision tree into a collection of rules. So you grow the tree, And then you convert it into a collection of rules, and rather than pruning branches, you prune entire rules and just treat it and let it go into a default. You prune rules and you say that you prune rules that somehow you find a way of defining complexity by the size of the rule or something like that. This is what C4.5 internally implements. Okay, so let me finally wrap up decision trees after this question.
When you say pruning, are you talking about like generalizing like a rule and then kind of like?
It could be pruning in multiple ways. It could be pruning by generalizing, by removing a certain condition, or it could be just erasing a rule and replacing it with just a default or something like that. There are multiple strategies for pruning. I'm not going to talk about pruning at all. I can point you to papers if you want. So let me finally wrap up decision trees. Exactly one lecture later than I had planned. So it's a rather popular machine learning tool. Machine learning goes through cycles of fashion, and today it may not be fashionable, but even 10 years ago it was quite fashionable. And who knows what's going to happen 10 years from now. The easy things about decision tree is that prediction is, or the good thing about a decision tree is that prediction is easy. Prediction is literally like asking 20 questions. You go down the tree. Once you have a tree, you just check each feature and you go down the path. And you get a label. The other nice thing about a decision tree is if you have a decision tree that is small enough, then that gives you an interpretable prediction. Not only do you have a label, you can also say the label is this because of these choices that happen. That interpretability argument goes out of the window if you have a tree with a million nodes. At that point, who knows what it means. But because of its interpretability, decision trees are often used as a way to explain the predictions of other classifiers, for example. So you build a decision tree to mimic another classifier. Decision trees can represent any Boolean function. Once you see a hypothesis space, you should ask yourself, how expressive is it? Decision trees, it turns out, is arbitrarily expressive in the among categorical functions. It can represent any Boolean function, which is good and bad news. The good news is that it can represent any Boolean function. It can learn anything. But be wary of hypothesis spaces that promise everything, because then exploring that hypothesis space becomes problematic. You have to, then it becomes a computational problem of how do you know how do you explore the entire space of all possible functions? That's one issue. The other one is if it is infinitely expressive, or if it's arbitrarily expressive, then not only will it capture the function that you want to learn, it will also perfectly remember all the noise that existed on the day that the data was collected. So be wary of that. That's the last point here, right? Decision trees are prone to overfitting. And so you should actively have some strategies in your decision tree learner that avoids overfitting. What we looked at from the learning point of view was one greedy heuristic called ID3. There are many variants of it because it's from the 1970s and we've had enough time to develop variants. But that doesn't mean that ID3 is actually a bad algorithm just because it's old. Most of the variants are built on top of this idea. It's useful to understand how it works because then you can actually use it as a sub-module in a larger learning system. For example, a cool idea, which you might actually be doing in a future homework, is to build decision trees of low depths no more than 2, and these are going to be feature extractors for another classifier that's built on top. Right? You could think of decision trees as learning low-level features. Okay, one thing that we did not cover at all was how decision trees can be used for regression. If you are interested in that, come talk to me and we can chat about that. And unfortunately, I'm not going to start linear classifiers today because I have a minute and that's about 3 lectures. So we'll look at linear classifiers on Tuesday. At this point, I've covered almost everything you need for the homework. pretty much, I think I've covered like 97% of what is needed. There's this tiny bit about linear classifier that still remains, and I'll cover that on Tuesday, and you can quickly do it right after that. Please get your homework done on time. We have office hours to help you out if you have any problems.